Preface to Physics series on Physics from Maximal Information Emanation, Variation, Propagation, and Emanation. This is a 7-book physics series that starts with classical mechanics, Book 1, then classical field theory such as electromagnetism, Book 2, then manifold dynamics, such as general relativity, Book 3. The switch to a quantum mechanics description is given in Book 4, and to a quantum field theory, QED in particular, in Book 5. A quantum manifold theory would be the obvious next step, except it cannot be done. There is not a renormalizable field theory for gravitation. Instead, a thermal quantum manifold theory is considered, as well as black hole thermodynamics in general, in Book 6. Book 7 describes a new theory, emanator theory, that provides a deeper mathematical construct that undergirds quantum theory. Much like quantum theory can be shown to provide a deeper, complexified, mathematical construct based on the classical theory. This is a modern exposition where subtleties of chaos theory are described in Book 1, of Lorentz invariance in Book 2, of covariant derivatives, general relativity, and gauge covariant derivatives, Yang-Mills field theory, in Book 3. Book 4 on quantum mechanics provides an extensive review of QM, then considers a full self-adjoint analysis on the full general relativistic solution to the spherical shell infall system, a result carried over from Book 3. Book 5 considers QFT basics in detail, along with alternate vacua in specific scenarios. Book 6 considers thermodynamics from the basics to the Hamiltonian thermodynamics of some black hole systems. Throughout, the odd recurrence of the alpha parameter is noted. In Book 7 we look to a deeper mathematical formulation from which the quantum path integral formulation would result, as well as explaining the odd parameters and structures that have been discovered, such as alpha and Lorentz invariance.
The physical description starts with the classic formulations of point-particle motion. The first approach to doing this is using differential equations, Newton's first and second law. The second is using a variational function formulation to select the differential equation, Lagrangian variation. The third is using a variational functional formulation, action formulation, to select the variational function formulation. Historically, it wasn't realized until much later that there are two domains for motion in many systems, non-chaotic and chaotic. In a description of particle motion, assuming not in a parameter domain with chaotic motion, several important limits are found to exist. Examples include the universal constants from the aforementioned chaos phenomenon that are still encountered in non-chaos regimes if driven to the edge of chaos. Limits are found where scattering is defined in the asymptotic limit, and perturbation theory is well defined in the sense that it is convergent. Overall, if the evolution is described as a process, it is often a martingale process, which has well-defined limits. So, we have descriptions for motion, typically reducible to an ordinary differential equation, ODE, and for which solutions, requiring limit definitions, are typically found to exist.
The physical description then contends with field dynamics in 2D, 3D, and 4D in Book 3. Two-dimensional, 2D, field dynamics can be described as a complex function that maps complex numbers to complex numbers. A novelty of the 2D complex function is it also shows how to handle many types of singularities, the residue theorem, thus provides important information about fundamental structures in physics as well as fundamental mathematical techniques for solving many integrals. For the 3D field dynamics, we do an analysis of the electromagnetic field in 3D. The level of coverage begins at an overview of electrostatics at the level of the graduate text Jackson. Some problems from Jackson chapters 1 to 3 are examined closely in developing the theory itself. For some, this material in Book 2 might provide a useful accompaniment to Jackson's text in a full course on EM, based from Jackson's text. A quick review of electrodynamics and electromagnetic wave phenomena is then given. In essence, we see many more examples of ODE problems with solutions, such as for the 3D Laplacian, usually involving separation of variables. We then review the famous transform, discovered by Lorentz in 1899, that relates the EM field as seen by two observers differing by a relative velocity. With the existence of this transform, that brings in the time dimension along with the relative velocity, we effectively have a 4D theory.
From Lorentz invariance we have, as a point transformation, rotational invariance under SO3 or SU2. If Lorentz invariance is fundamental, then we should see both forms of rotation invariance, one of vector/tensor type from SO 3, and one of spinorial type from SU 2. This is the case, as gauge fields are vectorial and matter fields are spinorial. From Lorentz invariance as a local invariance we have the Minkowski, flat, spacetime metric, which then generalizes to the Riemannian metric, in general relativity. As with the point-particle dynamics, for the field dynamics we have three ways to formulate the behavior: 1. Differential equation, 2. Function variation, on Lagrangian, and 3. Functional variation, on the action. We will see similar limit phenomena as before, but also new phenomena, including inevitable BH singularity formation, the Penrose singularity theorem, 2. FRW universe formation, from homogeneity and isotropy, 3. The BH collapse singularity, 4. The atomic collapse radiative singularity. Classical dynamics, thus, has two field-like formulations to describe the world, field and manifold. Such formulations can be interrelated mathematically, so what is happening is more a matter of physics and convenience. On this difference, that appears to be no difference, mathematically, is that different physical phenomenologies are at play. Field descriptions appear to work for matter, where the fundamental elements are spinorial. Manifold descriptions appear to work best for geometrodynamics, GR, where the fundamental elements are vectorial, or tensorial, such as the metric. Matter fields are renormalizable, thus quantizable in the standard QFT formulation, to be described in Book 5, while gravitational manifolds are not renormalizable, and have constraints, weak energy condition and positive energy condition given the existence of spinor fields on the manifold.
The presentation in Books 1 to 3 on classical physics is partly done to make the transition to quantum physics simple, obvious, and in some cases trivial. Consider the functional variation, action formulation of the behavior, whether point particle or field. This can be captured in integral form, as was done by D'Alembert very early, then by Laplace. Note the use of a large constant to affect a highly damped integral for selection purposes, on variational extremum of the action. To transition to the quantum theory we also have the large constant from 1/h, and so the only difference is the introduction of a factor of I to affect a highly oscillatory integral for selection purposes. After the transition to a quantum theory, for the point-particle descriptions, the classical collapse problem for atomic nuclei is eliminated. The spectral predictions have excellent agreement with theory, but there is still fine structure in the spectra not fully explained. The theory is not relativistic and some initial corrections for this are possible, without going to a field theory, and these indicate closer agreement and explain most of the fine structure constant discrepancy, and reveal alpha in another place in the theory. It is shown in Book 3 and Book 4 that the GR singularity problem, however, remains unresolved for the test case of spherical dust shell collapse, done in a full GR analysis, then quantized in a full self-adjoint quantization analysis.
In Book 5, the transition to quantum theory is continued to the field theory descriptions. A precise description/agreement of atomic nuclei is now possible with QED, and within the nuclei themselves, quark confinement, with QCD. The field theories have a small set of bothersome infinities, however, which is eventually solved by renormalization. As mentioned, the quantization of manifold theories, such as GR, does not appear to be possible due to non-renormalizability. Not to be deterred, in Book 6 we consider a Hamiltonian description of a GR system whose quantization would involve an energy spectrum based on that Hamiltonian. If we then use analytic continuation to take us to the thermal ensemble theory based on the partition function that results, we can consider the thermal quantum gravity, TQG, of such systems. This last example, from Book 6, showing a consistent TQG theory if we use analyticity, is part of a long sequence of successful maneuvers involving analytic continuations in different settings. What is indicated is the presence of an actual complex structure to the stated theory. There is the trivial complex structure extension mentioned above that brought us from the standard classical physics theory to the standard path integral quantum theory. But we also see actual complex structure at the component level with time complexation, that ties to thermal version of the theory by defining the partition function, and we have complex structure as the dimension level in the form of the successfully applied dimensional regularization procedure used in the renormalization program.
As well as covering the breadth of core physics topics at both undergraduate and graduate level, for courses taken at Caltech and Oxford, including extensive presentation of problems and their solutions. The series also examines, in specific cases, the boundaries of the physical world from the inside, and then later from the outside. To this end, exploration of spherical dust collapse to form a singularity is examined in a fully general relativistic formalism, and then carried over to a quantum mini-superspace, quantum gravity, analysis, in books 3 and 4. Also examined in depth are the topics of black hole thermodynamics and quantum field theory with alternate vacua. Part of books 5 and 6. The in-depth material comprises the topics covered in my PhD dissertation, portions of which are published. In recent work on machine learning, that includes statistical learning on neuromanifolds, we find a possible new source for a foundational element for statistical mechanics, entropy, via seeking a minimal learning process/path on a neuromanifold. By the time the series reaches thermodynamics in Book 6, therefore, the foundational thermodynamics elements have all been established from the physical descriptions discovered in Books 1 to 5, they just haven't been put together in a comprehensive analysis that gives us the fundamental constructs of thermodynamics and statistical mechanics. That said, it would seem that thermodynamics is, thus, entirely derivative from other, truly fundamental theories. Not so. In the joining of the parts to make thermodynamics we have something greater than the sum of the parts. In the system descriptions we find that emergent phenomena exist. This, at least, is unique to thermodynamics, so it is fundamental in this sum greater than the parts aspect.
In Book 7, the last of the series, we consider the standard physical world, described by modern physics. From the outside. In doing this we've already eliminated part of the mystery of entropy by the geometric neuromanifold description. If we can understand other oddities of the standard theory, and arrive at them naturally, then we might have an even deeper dive into modern physics, testing the limits of what is possible, and see possible future developments and unifications of the theory. This is what is described in papers, and organized along with current results into the final book of the series. Efforts in the last book of the series involve choices and concepts identified in the prior 6 books of the series, and theoretical maneuvers gleaned from the most advanced courses in physics and mathematical physics taken while at Caltech, as an undergraduate, and then as a graduate, and the Oxford Mathematics Institute, as a graduate, and the University of Wisconsin at Milwaukee, as a graduate. The broad range of topics covered in the series is, initially, similar to the Landau and Lifshitz graduate textbook series, see reference 27, with a similar exposition on classical mechanics at the start of Book 1. Even with well-established classical mechanics, however, there are significant, modern, updates, such as modern chaos theory. In the final 2 books of the series, Books 6 and 7, we arrive at statistical mechanics and thermodynamics, together with modern topics such as black hole thermodynamics, thermal quantum gravity, and emanator theory.
Key constants and structures of physics, their discovery from the experimental data, and their theoretical placement in the grand scheme, are emphasized throughout the series. The constant alpha, aka the fine structure constant, appears in numerous settings, so special note of the occurrence of alpha will be made in each chapter. This is the case even at the outset with Book 1, due to fundamental numerical constants appearing from chaos theory. In Book 7 we see the origin of alpha, as a maximal perturbation amount, appears naturally in a formalism for maximal information emanation. But maximal perturbation in what space and in what manner? In Book 7 of the series we will see a possible representation of such an information entity and its space of existence in terms of chiral trigintiduonians. Thus, in the end, this is an effort to tell of a journey to a special place, where many paths and errands meet, giving rise to emanator theory and an answer to the mystery of alpha. Part of this journey is equivalent to finding the Arkenstone, alpha, in the most unlikely of places, the trigintiduonian emanation mathematics underpinning the emanator formalism, a.g., Smog's lair, described in Book 7. Why I should have wandered into such an odd place, mathematically speaking, and why I should posit a deeper form of quantum propagation using hypercomplex trigintiduonians, here called emanation, is why there is such extensive background on standard topics. This extensive background even impacts the classical mechanics description via its modern chaos theory material, due to a possible relation between C sub infinity and alpha. The critical role of emergent phenomena is only understood at the end, including for manifolds in geometry and neuromanifolds in statistical mechanics, and leads to a book 6 that goes from very basic initial thermodynamics to very advanced emergent phenomena. Much is made clear with emanator theory, including how reality is both fractal and emergent. At this point in the journey, as with Tolkien, this much I can say: the road goes ever on, and whither then? I cannot say.
The 7 books in the series are as follows. Book 1. Classical Mechanics and Chaos Book 2. Classical Field Theory Book 3. Classical Manifold Theory Book 4. Quantum Mechanics and the Path Integral Foundation Book 5. Quantum Field Theory and the Standard Model Book 6. Thermal and Statistical Mechanics, and Black Hole Thermodynamics Book 7. Maximum Information Emanation and Emanator Theory.